During your presentation, you described a pathogenic protein interacting with an enormous number of molecules. What makes this protein so versatile in its interaction, and how does this contribute to disease mechanism?
Well, transthyretin is a serum protein synthesized mainly by the liver and secreted into the bloodstream. It is enriched in beta-keto sheet structures, which are in itself increase the risk of forming amyloid fibers. So it's already the protein itself carries the risk of forming amyloid fibrils. And it's the protein where, when it has mutations, that they increase the risk of amyloid formation. So this is the protein which in itself carries the propensity to form amyloid. Secondly, it's a serum protein, so it's transported by the bloodstream from the liver to diverse organs. It transports retinol, vitamin A, thyroxine, so its transport protein is, and usually transport proteins are able to change their conformation, making it more volatile to form secondary structures which lead to amyloid formation. And then it interacts at the diverse tissue sites, interact with other proteins which may influence the conformation of the protein, destabilizing it and increasing the risk of amyloid formation. It's a very complex disease. We have not understood everything which happens in the organ at the diverse anatomical sites, but we know of different mechanisms contribute to the amyloid formation. Whether they take place always in each organ site and in each patient, we don't know. But we know that metal ions, pH, chaperones, molecules which more or less stabilize or destabilize the protein conformation contribute to the disease.
Studying a protein with potentially millions of interactions seems incredibly challenging. Which experimental or computational approaches have proven most effective in mapping these interactions?
Well, that's a difficult questions. In the last 10 to 20 years, proteomics analysis have unraveled a lot of the mechanisms which might be involved in amyloid formation. I think we still are not really using proteomics to decipher disease mechanisms, but I think that's the best way, because there we get an idea how complex the disease is at the specific anatomical site. And we've discovered many proteins which are specifically enriched, and by deciphering the biological mechanism in which these proteins are contributing or involved may help us to understand the disease and its pathogenesis. For instance, we have found more than 80 different proteins, peptides within ATTR amyloid. Some are members of the complement system, and having detected them within the amyloid, raised the question whether the complement system is actually participating, activating in ATTR amyloidosis. So I think proteomics helps us to find or just, identify proteins, peptides, which are associated with the disease, and by that way also identify with computational techniques which biological mechanisms are involved in the disease.
Understanding such a complex network of interaction, how can this knowledge guide the development of target therapies or intervention for related disease?
I think the same path, once you have identified biological processes which are involved in amyloid formation, then you may find new treatment angles, such as, proteolysis has been a matter, but it could also be that if once you identify the complement system to be activated or involved in amyloid formation, you may consider new treatment options to, avoid or improve complement activation. Can be beneficial, can be deleterious, we don't yet know. But once you have identified which role it plays, you may then find a new treatment angle.